Okay, everybody, welcome to day 2 of chemistry. I've had a fair amount of emails. I know there's, I'm sure, a ton I have forgotten to tell you. Just this being the first time of you being first semester students, not familiar at all with the flow and how things go, and Blackboard being all new and that. But just a couple things that I want to mention. If you're thinking of any other questions too, write them down for tomorrow's meeting. So tomorrow we have a Zoom meeting at 9, and I'll be on there. So Justin, Nicole, all of us should be on there. So you can have, shout out more questions. Science unfortunately does not have a textbook. It doesn't have a designated textbook. So I pull material from different resources. I gave you guys a link of a resource that I've used here in this PowerPoint. I have it in my speaker notes, and then I provide the link for you. It's like, I can't even remember the name of it, building blocks. Let me see if I can find it again. Here it is. Atoms, isotopes, ions, and molecules, the building blocks. Okay, so I knew it was from a biology book, it looks like, from OpenStack. So I went ahead. Don't freak out, it's a lot more than you need to know, but it's just another resource to help you out with some terminology. So these first couple lectures a lot of it is terminology. Kind of a review from way back in the day if you took chemistry, about atoms and ions and bonds and all that kind of stuff. I also, on this particular day for day 2, I also put a link for a Quizlet. Okay, a Quizlet is a study guide that a lot of us use, or a study tool, and we use it for like test review and stuff. So a quiz review. So if you look at day 2 under chemistry, again you're going to see the original PowerPoint that was done without the audio, and sometimes those are helpful to look at, especially if there's links. Okay, and then the second bullet or whatever, tab, whatever you want to call it, has that link rather to the OpenStax for that a resource I was just telling you about. And then there's your Quizlet link, and I believe there's 15 terms on there, and that's going to give you a pretty good idea what you want to study for your first test. If I remember right, it's not really, the exam's not that big, it's just again a lot of terminology. Then you will have some metric practice, and there is a metric conversion chart also listed there. So metric practice, I would like you to work on that over the weekend. Do your best with it. You can use there's conversion tables and conversion tools out there to help you, and we'll spend more time with that again in math. The other assignment that you have is the article review, and that's just basically a takeaway. I just want a paragraph, obviously typed or written if you want to hand write it, and just send me a picture of it, whatever. But it just is an article that's I don't know, half a dozen or so pages long. What does chemistry have to do with biology? So it's just, I just want you to reflect on it. I want you just to tell me what you learned about it, or what you didn't know, before, like a takeaway, basically. Okay. All right. So hopefully that clears up a few things for you guys. I know this is very hard, and my apologies, but unfortunately there's nothing we can really do about it at this point. So keep our fingers crossed. We'll be back on campus in some shape or format the middle of May. Just kind of see how it goes. So again, a lot of terms, things that you may have never heard of, or things that are going to be reviewed. So atoms, molecules, and more. Oh, and the other thing I want to say, because I've had some questions about physics physics is not going to start. If you look at the calendar, which is under the course syllabus tab there, way to your left, physics doesn't start till about the middle of May. So, all right. Okay, so some of the things that we're going to kind of touch on about atoms, defining them, how they bond to form molecules, water, and how it's the basis for a lot of solutions in the body, acids and bases, and how they are measured by pH. And we'll talk a lot about acids and bases and pH as you go through the program. Organic molecules and their importance in the body, and then chemical reactions such as cellular respiration. So the acids and bases and the organic stuff and the cellular respiration, that's going to be an upcoming lecture, so that's not quite so much today, but this is kind of what's kind of coming down the pipe. Today is mainly kind of more atoms, defining them, ions, and such. Alright, so matter is anything that takes up space and has mass. Okay, so all solids, liquids, and gases are composed of matter. Know that definition. That is definitely a test question. Okay, all matter is made of atoms, and atoms are the building blocks of matter. It's an analogy of how bricks are the building blocks to houses. Okay, so an atom is the smallest unit of matter that retains all of the chemical properties of an element. Okay. So when we look at an atom, okay, we remember from way back when, we have a positive, the proton is the positive part, neutron is always neutral or no charge, and then electron is your negative charge. Okay, so there's three parts of an atom: proton, neutrons, and electrons. Okay, so remember what those all mean. Proton being positive, electron being negative, and neutron neutral. Okay, so the protons and the neutrons are found then in the center of the atom, which is called the nucleus. Okay, and then the electrons orbit or circle around the nucleus. So just kind of a little refresher there on atoms. So back to elements. Elements then, what are elements? The purest form of matter is an element, and each element is made of atoms. Elements are unique forms of matter with specific chemical and physical properties that cannot be broken down into smaller substances by ordinary chemical reactions. Okay, so there are 118 elements, but 92 of them occur naturally. The rest of them are made in a lab and are considered unstable. The four common elements to all living organisms are oxygen, carbon, hydrogen, and nitrogen. Okay, so those are just the abbreviations there that you should start to recognize. Elements are the alphabet to the language of molecules listed by the periodic table, and they're listed by their composition and their chemical properties. While the atoms may have different weights and organization, they are all built the same way. So for example, if we take a look at gold, okay, a solid gold coin is a solid metal at room temperature. And a gold coin basically is a large number of gold atoms that have just been molded together into a coin and a small amount of impurities. Gold atoms can't be broken down into anything smaller while still retaining their properties of gold. Okay, so now we're looking at, again, I mentioned the living organisms, the four common elements, and here are the same ones mentioned that are present in your body, and the percentage of total body mass. So I thought this was kind of interesting. I'm trying to remember if I found that in the article that I gave you, but I found this, I think it was a textbook actually. I used my son's chemistry textbook. Oh, actually it's right here. I wrote it right there. That's where I found it. Probably my anatomy and physiology textbook from years ago. That's where I found this. So your anatomy and physiology book too that you have for A&P, that has definitely the first, I don't know, within the first couple of chapters has information on this too. So, you know, use that as a resource if that helps you. So, 65% of our body is made up of oxygen. It's a constituent of water and organic molecules needed for cellular respiration, which then produces ATP. And I know Nicole touches on that, I believe, too. Carbon is found in every organic molecule. Okay, that's what makes it organic, is that carbon. Hydrogen is 9.5% of total body mass, with carbon being second. Constituent of water, obviously H2O, all foods and most organic molecules. Contributes to the acidity when it is positively charged, so H positive, hydrogen positive. We'll talk about that later when we're talking about acids and bases. And then nitrogen being the fourth one as far as order of appearance or how much, is the component of all proteins and nucleic acid. The nucleic acids in our DNA and RNA. Alright, so kind of going back a little bit to the periodic table and how to kind of read it. And I know we talked a little bit about it on the last lecture, but this is just kind of going over it again as we're looking at oxygen here. So our atomic number then is on the top, is above the symbol. So we have 8. That is the number of protons, and it's also the number of electrons in an atom of an element. Okay, so O is the symbol, oxygen's the name, and then the atomic mass / weight is is 16, which is then the number of protons plus neutrons. So we're going to look now. This is going to be lithium. So we're looking at it and pretending we want to kind of draw it out. Okay, so we're going to first look to the right side, excuse me. So we have lithium, we have the symbol, the number 3 is representing the number of protons, and then our 7 there is our atomic mass. So the way we figure out how many neutrons we have is we take the atomic mass minus the number of protons, okay, and then that gives us 4, which equals the number of neutrons. Okay, so to determine the number of protons, we look at the atomic number, and then how to determine the number of neutrons, we look at the atomic mass minus the atomic number, and then you get your number of neutrons. Okay, so we have then if we're drawing this out, we have 3 electrons. Okay, that is the same amount of protons. Okay, and we've got the positive protons in the middle, and then the negative electrons are in the shell. Okay, so we have 2 in the first shell, or the first layer, the part that's closest to the nucleus, and then 1 in the outer shell. And we'll talk about how they kind of interact and trade off. Alright, so atoms always have as many electrons as protons. Atoms usually have about as many neutrons as protons. Okay, so when we're adding a proton, it makes a new kind of atom. Okay, and adding a neutron makes an isotope of that atom, or a heavier version of that atom. I'll talk more here in a few minutes about isotopes. Okay, so if we're looking at this here, we're kind of comparing hydrogen, helium, and carbon. All right, so the atomic number then is basically your number of protons. Okay, so your atomic number is equal to the same amount of protons. So if you were to look at the periodic table of elements, the number that would be above the symbol would be 1 for hydrogen, 2 for helium, and 6 for carbon. Okay, but that also equals the number of protons. Okay, then the amount of electrons equals the same amount of protons. Okay, I know this gets confusing. And then we're looking at neutrons. Hydrogen happens to have no neutrons, okay? But it has helium has 2 neutrons and 6 electrons. So just kind of comparing the 3 of these elements here. Now, again, kind of going back to isotopes, we're defining them a little bit more. Isotopes of an element are atoms that have the same number of protons as every other atom of the element, but it has a different number of neutrons. Okay, so there are 2 main types of isotopes. We have radioactive and stable isotopes. So stable isotopes have a stable combination of protons and neutrons, and so they have a stable nuclei and don't undergo any type of decay. So carbon, potassium, and calcium are examples of that. Some isotopes are unstable and freely emit particles to get them to a more stable form. So if they do, in that process, they are called radioisotopes, and then their decay is called radioactivity. Okay, and we use some of these radioisotopes in medicine for diagnosis and for treatment of diseases. So for example, for diagnostic purposes, a person's thyroid gland quickly takes up the radioisotope of iodine. Okay, so the radiation given off by that isotope causes then the thyroid to be visible on an X-ray, so they can see if there's any abnormalities going on. For treatments, sometimes they go ahead and they actually plant in different seeds of radioisotopes or radioactive seeds to different tumor sites, so that they're really specific to that type of cancer cell, and hopefully their radiation can kill off those cells. So those are just kind of 2 different examples of how we use radioisotopes in medicine. Alright, looking at molecules again. So the molecule sodium chloride is table salt. When placed in water, the ionically bonded molecules separate into their individual ions. Okay, and then these ions in the solution, remember ions in the solution are called electrolytes, and they are actually capable of conducting electricity. Okay, so again, a lot of this is terminology. Rewrite out your notes, go back through. I try to bold things on terminology, and plus your Quizlet will help you study that too. So some examples of electrolytes can be sodium, potassium, calcium, and chloride. Okay, and it's very important to maintain that electrolyte balance. That's part of the blood work that they do when you're admitted to, obviously to a hospital, the ER, or even at a clinic, a doctor's appointment. They'll check your electrolytes, especially if you're on different medications, because sometimes they can alter that. Alright, so atoms with a charge are called ions, and ions are attracted to each other because they have opposite charges. So they form a bond, okay, resulting in an electrically neutral molecule. So the positive and the negative attract to each other, and then because they have formed that bond, then it's considered electrically neutral. Okay, so a positive ion is called a cation, and a negative ion is called an anion. So make sure you know that terminology also, so be able to define a cation and an anion. Okay, and I know, like I said, this is a lot. It's just terminology that you're going to become familiar with, so that we're going to build off of this. We're not going to spend a real lot of time dissecting this all, out. Like that link is a lot more in depth than you really are going to know, but it's just kind of forming a little bit of a foundation here. So again, ions in a solution are called electrolytes. Okay, so make sure you have electrolytes down as a terminology also. Right, so atoms will bind with other atoms again to form molecules in order to fill their outer shells with electrons. So if their outer shells are filled, then it makes them more stable. So again, the definition of a molecule is two or more atoms bonded together. And a covalent bond is your most stable type of bond, okay, which is often formed by carbon atoms. So this occurs when two or more atoms share electrons to fill their outer shells. So remember that a covalent bond is your most stable bond. Another type of bond is an ionic bond, and this is where two or more atoms bind to form a molecule by giving up or receiving electrons from each other's outer shell to fill their outer shell. Okay. The transfer of these electrons means each of the individual atoms is no longer electrically neutral. Okay. So again, two or more atoms bind to form a molecule giving up or receiving electrons from each other to fill their outer shells. So for example, in sodium chloride, typically form an ionic bond. The sodium atom gives up an electron and becomes positively charged, while the chlorine atom receives the electron and becomes negatively charged. Sodium is positive and chloride is negative. So again, your covalent bonds are the strongest. Okay, polar bonds are two atoms having a covalent bond that can exert different attractions for electrons in that bond. This can actually cause an unevenly distributed charge. This means typically there is one side of the molecule slightly negatively charged, and the other side is slightly positively charged. So an example is water. The oxygen has a slightly positive charge and the hydrogen has a slight negative charge. Polar bonds are the reason that some substances actually dissolve readily in water and others don't. Hydrogen is a weak bond between two molecules resulting from electrostatic attraction between a proton in one molecule and an electron negative atom in the other. Water is an example of hydrogen bonding. Okay, just knowing that hydrogen bonding is a weaker bond. It's weaker than a covalent or an ionic bond, and it takes less energy to break that. Okay, so it takes less energy to break a hydrogen bonding. Okay, so it's weaker than a covalent or an ionic bond. The bond is actually, when you think of water, the bond is between the hydrogen of one water molecule and the oxygen of another water molecule, not between the two hydrogen atoms. Okay, that's kind of a misconception because you think H2O, that it's, well, there's two hydrogens, but you think it's between the two hydrogens. It's actually the bond between the hydrogen of one water molecule and the oxygen atoms of another water molecule that actually makes that bonding. Okay, so here is an example of looking at covalent bonds sharing electrons, this being H2O, so this is water. So you see where the covalent bond is there on the outer shell of the oxygen. Okay, ionic bonds. Ionic bonds then involve a transfer of an electron. One atom gains an electron while another loses. Okay, I think we kind of already said this a little bit, but this makes one electron then have a negative bond. Remember, negative is an anion, and one have a positive bond, which is a cation. So know that terminology. Know that anion is negative, cation is positive. Okay. Certain ions are important in human physiology, like again, I mentioned sodium, potassium, and calcium. They are necessary for nerve impulse conduction, muscle contraction, including your heart, and fluid balance. Okay, and so a lot of sports drinks have these in them to help, supplement. And this is just kind of a diagram, kind of showing the transfer of the electron there in the ionic bond and sodium and chloride. So you can see how it goes from sodium to the chloride. So how the outermost shell of the sodium just has that one, so it wants to go over to chloride to help fill its outer shell, and then it makes it more of a stable, so that it's sodium chloride. Okay, hopefully that wasn't too terribly too much. And we'll see you next time. Thank you.